Hi, my name is Guoshi Li, and I am presenting my work, Effective Connectome over Human Lifespan. As we know, human connection depend on the complex interaction of vast number of distributed circuit and network. Human connectome aim to delineate the anatomical wiring diagram and the functional operational principle of the brain. As the two major components of human connectome, structural connectome and functional connectome are driven by two major imaging modalities, diffusion MRI and functional MRI. The structural connectivity describes the long-distance wire vector track that connect distinct brain regions. On the other hand, functional connectivity characterizes the statistical dependency among fluctuating ball time series from the distributed brain region. However, functional connectivity have some notable limitations. First, functional connectivity is undirected and symmetric, which cannot model the asymmetric brain structure. Also, functional connectivity is essentially descriptive, so does not allow for mechanistic account of the neuronal circuit. By comparison, effective connectivity is defined as the direct causal influence among neuronal population. Because the effective connectivity builds on a generative model of neural interaction, it can potentially provide mechanistic neuronal account of the MRI data. The major goal of this study is to characterize the evolutionary development of effective connectivity over human lifespan based on large cohort of resting state functional MRI. Such characterization can provide mechanistic understanding of neural circuit interaction during development. It can also provide standardized assessment of individual growth and early detection of DE. We used 4 datasets for this study. The Baby Connectome Project with 278 subjects and 504 longitudinal scans. The HCP development with 636 subjects. The HCP young adult with 1,062 subjects. And the HCP agent with 686 subjects. This will give a total of 2,665 subjects with 2,891 scans. The BCP data was processed using an infant dedicated pipeline, while the HCP data was processed using the HCP pipeline. The 4 time series were extracted using the Desiccant Delineating atlas with 68 cortical regions. The 68 cortical regions were grouped into 6 functional networks, including the visual network, somatomotor network, saline network, limbic network, frontoparietal control network, and deformal network. We apply regression dynamic causal modeling to estimate the effective connectivity. Regression DCM employs a linear DCM model. It converts the linear DCM equation from the time domain to the frequency domain using Fourier transformation. It replaces the nonlinear hemodynamic model with a linear hemodynamic response function and assumes partial independence between connectivity parameters. With this assumption, regression DCM treats the model inversion in DCM as a special case of Bayesian linear regression problem. As a result, regression DCM is computationally highly efficient. It can invert whole brain network with more than 200 nodes within just a few minutes. We use the generalized additive mixed effect model to characterize the effective connectivity trains. In this equation, the Yij represents the measurement of the subject I at the J scale. Hij is the age of subject I at the J scale. Sex I is the sex of the I subject. Alpha I is the random intercept effect for the eye subject. Beta I is the random intercept effect for the size of the eye subject. F and G are the qubit spike function, and Eij represent the random Gaussian noise. We use several methods to describe effective connectome. First one is nodal effective connectivity. It is the sum of incoming effective connectivity to each brain region. The mean nodal effective connectivity is the average of the nodal effective connectivity among the 68 regions. The network effective connectivity is the average of the nodal effective connectivity for a particular network. The within network effective connectivity is computed as the average effective connectivity within a particular network. And between network effective connectivity is the average effective connectivity between a network and all other networks. These 7 figures shows the average effective connectivity at different development phases, including infancy, early childhood, late childhood, adolescence, young adult, middle adulthood, and late adulthood. We can see the effective connectivity shows the modular structure, where the effective connectivity within a network is higher than the effective connectivity between networks. Also, we can see the effective connectivity increase from infancy toward young adulthood before decreasing with age. The figure on the left shows the mean nodal effective connectivity of all the subjects over the lifespan. And the figure on the right shows the normative trajectory of the mean nodal effective connectivity for male and female. We can observe the mean nodal effective connectivity follow an inverted usage trajectory with the peak at around 9 years old. Also, the female nodal effective connectivity show a larger decrease during the early childhood, a faster increase during late childhood, and faster decrease at a later age. These 2 figures shows the network effective connectivity for the male and female respectively. We can see the network effective connectivity become more homogeneous with age. Also, the frontal parietal control network and the limbic network show the largest and high and the lowest effective connectivity respectively. These 2 figures shows the within network effective connectivity for male and female respectively. We can see the within network effective connectivity maintain a stable hierarchy during development. Specifically, the sensory system, including the visual and somatomotor network, maintain a higher within network effective connectivity than higher order network, including frontal parietal control network, deformal network, and saline network. Moreover, we can see the frontal parietal control network is resistant to decay during the middle and late adulthood. These 2 figures shows the between network effective connectivity for male and female respectively. We can observe that the between network effective connectivity of all the network except the limbic network can persist after reaching the peak value. In addition, the higher order network, including frontal parietal control, deformal, and saline network, maintain a stronger between network effective connectivity than the sensory system throughout the lifespan. In summary, we saw the effective connectome mature during late childhood and adolescence, consistent with the critical development period. Also, network effective connectivity become more homogeneous with age, suggesting more network integration as the brain age. Moreover, we saw the higher order network, including frontal parietal control, deformal, and saline network, have larger between network effective connectivity, but lower within network effective connectivity than the primary sensory system, indicating a more active role in network integration than network segregation. Lastly, research the frontal parietal control network is the most resistant network to agent-related degradation, while the limbic network is most vulnerable to agent-dependent declines. Thank you for the attention. If you have any question or comment, please feel free to contact us.